I cannot reject null hypothesis at 95% confidence. What is the exact percentage with which I can reject the null hypothesis? That is my question. In here you are simply fixing alpha, right? You are fixing alpha and saying I want to be 95% sure. Take this example, the previous case. How much percentage are you sure in this case? The answer is around 10.94. The rejection ratio region is beyond 1.96, but you are telling me that it is 10.94. So what is the value, what percentage I can be sure? I am sure 95%, but what is the exact confidence with which I can reject the null hypothesis in this case? 10.96. Can anybody go to the table and look? Do you have the normal table? No, none of you. Then I have to do parallel. So this is the standard normal, right? So 1.96, 10 point is not even there. So what are we telling? We are rejecting with almost like 99.9999% confidence. You are able to reject with very high confidence, the first example, because 1.96 we know what it is, okay. So 1.96 is what my Z alpha is by 2, 1.96. if I look at this is what here, right, that is 95%. Where is 10? 10 is not even there, okay. So it is there, this table does not have, of course it is not 100%, it will be very small value, alpha will be, or the probability with which you can reject will be very high, okay. So what we call that is the p value of a test, we call it as p value of a test. Suppose your z is 2.12, okay. Suppose your z calculated z is 2.12. You can reject H naught at the, what is z at z alpha by 2 for 95%? It is 1.96. Your z is 2.2. Let us say your calculated z is 2.12. The z star, whatever test statistic you calculate is 2.12. So it is, you can reject at 95%, but you cannot reject at 99%. At 99% the value will be like 2.18 something, okay. So you cannot reject at 98, but you can reject at you cannot reject at 99, but you can reject at 95, right. So what is the exact percentage of confidence with which you can reject the null hypothesis? That is what is called as p value. It is a very important number in your, when you do computations. Of course we will do little bit of computations using Python, or probably we will do using Python, not R, okay. Let us learn one software proper. I will ask my TA to do some examples using Python, okay, confidence test of this thing. So p value is the exact, or 1 minus p value is the exact confidence percentage with which you can reject the null hypothesis. So this is a very important number. Why? Instead of saying 95, 99, I want to know how much percentage I can be sure about rejecting the null hypothesis. Sometimes it may turn out to be 75, sometimes it may, depending upon the need, it could be very high or low depending upon the problem at hand. So knowing p value is a very important part of this confidence testing, because that will also give you an idea about how much extra samples probably I may need to do, or how much experiments do I need to do to get the p value close to whatever I want, okay. So this 1 minus p percentage is the exact confidence with which I can reject the null hypothesis. So in this example, previous example, okay, suppose my mu is 65,000, instead of mu naught is 65,000 and now it changed to 61,000. So what happened? My Z value is minus 1.615. Okay. Can I reject or accept the null hypothesis at what percentage of confidence? Here we are talking about exact one. So what is the confidence? I can reject with Z greater than 1.65 is 0.047. It is not 0.05, it is 0.047. Alpha by 2 is what? Alpha by 2 is 0.047. You can go and look at the tables. So this value is 1.675, right? 1.67 and of course 5 you can approximate somewhere, average it. So 0.047. What is the confidence with which I can reject? What is the confidence with which you can reject? Tell me here, what is the confidence with which you can reject the null hypothesis? So 1 minus alpha, right? 1 minus, this is into 2, right? Z alpha by 2. If you take it as Z alpha, this is Z alpha, 1 minus alpha percentage is my confidence with which I can reject. So this is what? 1 minus, yeah, you can reject with 95 point because it is one sided. It is one sided hypothesis. If I take two sided, what will be the answer? This is two sided, one sided. If it is two sided, it will be less than, right? If it is, this is one sided, I have taken 1.67, okay. So remember 1.96 is 0.025, 0.025 into 2 is what? 0.5. This is, if I take this as alpha by 2, Z alpha by 2, what is the percentage with which I can reject? 0.047 into 2 is what? 0.094. What is the percentage of confidence with which I can reject? 91. Okay. So you will have to know the exact p value. See, it is not bad, you are not way off. Instead of 95 you are 91 percentage. Okay. So this, knowing this p value is a key. Okay. Remember my mu naught, my, this is a two sided hypothesis. So my, this should be alpha by 2. Okay. So p value is 0.9094, that is what? 0.047 into 2. If it is a one sided hypothesis, you are going beyond 95. If it is a two sided hypothesis, you are actually 91 percentage only confident, right? But it is not as bad as you think, right? It is not as bad as you think, it is 91 percentage you are confident. If you make it to one sided, you will be more than 95 percentage sure. Okay. So it all depends on, so this p value is a very, very important quantity. Any statistical tool will give you not only alpha but also will tell you the p value. Okay. The higher the p value, so the smaller the p value, the better it is, because the confidence is, exact confidence is 1 minus p percentage. Okay. Alpha is we fixing it, p is the original number that comes out after doing the sampling and calculation. Okay. So reporting the test results, you always say p value, and if the p value is less than or equals to alpha, you reject H naught, and if the p value is greater than alpha, you do not reject H naught. Very simple. Okay. Now the results you tell in terms of p value, calculate the p value, and if the p value is greater than alpha, you reject the, less than alpha you reject the null, because you are even more sure than the alpha value. If p value is greater than or equals to alpha, then you say I will not be able to reject the null hypothesis. But this also gives you an idea how much I am confident. Am I very far or am I close? That is what p value tells you. Clear? Shall we move on? So that completes our learning of large sample population and all the related issues. You should be able to do the same for proportions. I told you proportions also you should be able to do, because proportions you know the p hat, you can estimate p hat from data, or p hat will be given to you, and your sigma p hat is known to you, that is nothing but square root of pq by n. So all of them are there, and that also follows a normal distribution for a large sample. And I have also defined what is a large sample, where p hat plus or minus 3 sigma lies between 0 to 1, clear. So for large population you should be able to do the same kind of studies for proportions also, okay. Now moving on to small samples. So small samples, if the sample is small and true sigma is unknown, this is what you have, it is t distribution instead of z distribution. What is the assumption? What is the clear assumption here? Underlying population is Gaussian, that is a very important assumption you make. Whereas in the previous case the underlying population is, what is the assumption you make? Central limit theorem, the underlying population is independent, IID, strictly precisely IID, but it can be just independent. Here it is a much bigger assumption, the underlying population is normal. So whenever you have got small samples, you have to test for the Gaussianity of the underlying distribution, otherwise you cannot, your t distribution will not work, is not supposed to be used, okay. So the same formula holds good, but t has, if you look at t distribution, so I have now one tail and two tail. What do I mean by one tail test and two tail test? When do we use one tail test? You all know what is tail, right? One tail test is for one sided hypothesis or one sided hypothesis. This is two tail test for two sided hypothesis, right. And I have given you the H naught alternate hypothesis, and the test statistic is t here instead of g star, it is going to be t x bar minus mu naught divided by s over root n, and rejection ratio, acceptance ratio also given. The only thing is the t alpha is based on n minus 1 degrees of freedom, okay. So what are the conditions? A random population is selected from the target population, the population from which the sample is selected is approximately normal, it is a key assumption, and the value of t alpha is based on n minus 1 degrees of freedom. So if you have n samples, okay, you should look for t alpha of, so if you know, if you look at the t table, I think I don't know, I have not given the t table here, okay. So you should be going and looking at your t tables, like z table, there is also a t table. I told you again, t cannot be solved using numerically because it is like normal distribution. After n greater than 30, t and normal become similar, okay. So t is also like normal distribution, so nobody would have solved a, what I call it as a closed loop solution, so they would have done for a standard t distribution, which is what we are doing, x bar minus mu by s over root n, right. So x bar minus mu, they would have by sigma, they would have solved it for standard t distribution, and t distribution depends upon n minus 1 degrees of freedom, I mean in this case n minus 1. So t distribution will have two things. If you look at the table, if you look at the table, it will be not just, here you have the probability cumulative distribution and the values, this will be for different degrees of freedom, okay. So the next class I will bring in the t table to show you, okay, it will depend upon the degrees of freedom, and of course you do not have many, you have only 30, right. So for 30 this is the value, for 29, 28, each row will have two things, okay. For 28 you have to look, 29 you have to look differently, etc, okay. So it will be two things, apart from z values and the cumulative distribution, it will also have degrees, the number of data points as one of the parameters. So this, the value of t alpha is based on n minus 1 degrees of freedom, okay. So you have to calculate t alpha comma what, that is all, you have to look for t alpha by 2 comma n minus 1. instead of just looking for alpha by 2 or alpha in your Z distribution, you have to look for corresponding to n minus 1. If there are 29 points, you have to look for T alpha by 2 corresponding to 28, and n minus 1 degrees of freedom, I told you, you are only already given x bar. So, basically it is n minus 1 degrees of freedom. Okay. So, this is your thing about small sample, okay, not large sample, but about small sample. So, this is a simple example. Okay. Suppose copiers average 100,000 between paper jams. So, between paper jams you have 100,000 copiers. Okay. Salesman claims these are better and offers to leave 5 units for testing. Okay. So, he claims that his copier machine is better than this 100,000 and leaves it to 5 machines for testing. Very natural, he is not going to give you 100 machines for testing, right. So, you have only 5, it is a small sample. Okay. The average number of copies between jams is 100,987. Now, with a standard deviation of 157, does this claim seem believable? You had 5 samples to test and you had an average of 100,987 with a standard deviation of 157. Does this claim seem believable? Okay. How do you pose it into a statistical problem? Mu s equals to mu naught is 100,000, and remember this is a one sided hypothesis. He claims it to be better, it is not changing, it is claiming to be better. So, this is one sided hypothesis, and you can calculate this x bar minus mu by s over root n. Okay. So, this is what I have, T value, and I have to go and look for T degrees of freedom equals to 4. Okay. So, what is my P value? So, P degrees of freedom equals to 4 is probability, P value is nothing but probability of degrees of freedom equals to greater than 0.06. That turned out to be how much? 0.0005. Okay. So, what is my 1 minus P percentage? 1 minus 0.0005. You can be very sure to reject the null hypothesis. You can believe his claim that his copier is doing better. Okay, because his value, P value is 0.005. Okay, his P value is 0.005. This should be equals to 0.05. Less than. Sorry. Less than, greater than is less than or equals to, this is my P value. 1 minus P percentage is 1 minus 0.05, 0.0005. So, you can be very sure that his machine is, his claim is good based on just the 5 samples, that is what it is. Make sense? So, this is a small sample T distribution problem. So, this is for proportions. Okay. Proportions again, Z is given, 2 tail test, 1 tail test, rejection ratio, rejection region, and your sigma p hat, q naught, everything is given, we all know this actually. Okay. So, the assumption is the random sample is selected from a binomial population because it is usually the case, because it is P or Q. So, it should be from binomial population. The sample size n is large, typically greater than 15, it is not even 30, it is greater than 15 is enough, large sample. Then you can apply this idea, because binomial distribution converges quickly to Gaussian compared to other distributions. I mean the x bar, the p hat converges to Gaussian very quickly, and that is why we said NP and NQ hat are both greater than or equals to 15. Okay. It will be around 30 samples, 40 samples, you can easily assume it to be Gaussian, and as x bar p hat to be Gaussian, and you can apply this. So, this is test of proportions. Okay. Large sample hypothesis test about population proportion. Clear? So, we have covered small sample, large sample testing of mu, mean mu, population mu, small sample testing of population mu, and we have covered large sample for proportions, okay. Then we will do examples and we will talk about type 2 probabilities with some bit of math, okay. So the next class we will talk about type 2 probabilities and some bit of math, okay, clear. Thank you folks.